So I want you to think of the next couple of segments as adding tools to our math toolkits that we're not going to use heavily for a little while. This particular set of authors feels like we better introduce them to this now so that when we need it later, it won't be quite as traumatic an experience. So, talking about labeling points in space. So coordinate space. So 3 dimensions. All right. So if you need that, 3 dimensions. Okay. So I'm going to do a little bit of sketching, but it's going to be more mathematically based when we get there. So our rectangular coordinates are x, y, and z variety, which we've already been using. So in this segment, we're going to look at a new type called cylindrical coordinates. So cylindrical coordinates would be more useful in space if you had certain shapes that would play to its advantage. So the name usually gives it away. In space, if the shape looks something like this, the x, y, and z coordinates usually are beneficial. So in this case, it's cylinder like you knew cylinder before recently, like the circular cylinder. It would benefit studying this kind of a shape, very much so. It would benefit studying this kind of a shape. And there are lots of things that we make that are more or less cylindrical shaped or wrapped around and rotated around an axis. So cylindrical coordinates, I have a nickname for them, but let's write them down first. The x and y are our polar coordinates, r and theta, and then z remains z. Z remains z. So I sometimes will nickname this type of coordinate system here polar plus z as just a little memory device for my mind to keep track of this. So cylindrical coordinates, you don't actually convert z at all. Z stays there, but the x and y become polar. So it is very useful in 3 dimensions to think about the top view. So what that means is the view you've always used, the traditional x and y look. So if I have a point here, that would be the radius and that would be theta in 2 dimensions. And then if there was a z coordinate, it would just be measuring how far above the paper is that point, or how far below the paper is that point. Nothing more than that. It's pretty simple. It's pretty simple. So I'm not going to spend a huge amount of time discussing the algebraic connections in these. I just want you to see enough to feel a little bit comfortable. It is very important that you are comfortable with polar coordinates. And you've had multiple courses that use polar coordinates before getting here. So this won't be too bad, this cylindrical coordinate project. Let's just leave that right there. Okay, so we have r, which is the radius in the xy plane. We have theta from the positive x-axis, and we have z, which is z. There's nothing else to that. So let's suppose I were to give you the following coordinates. Example here, and we will have the rectangular coordinate, and we will convert it to cylindrical coordinates. So if I had the point 0, 5, 0 in rectangular coordinates, the z coordinate should automatically be the z coordinate. There is no thinking about this process. But I always counsel my students in trigonometry all the way up to this level, no matter which course you do polar coordinates, if you're not willing to sketch a little bit of a picture, you deserve to be fooled. Your calculator will not help you. If I pick, for example, the sine function will not work in quadrant 2 if you're trying to find an angle, or quadrant 3. Your picture with a calculator are the combined skills you might need, or your picture plus some old memory devices. So in this particular problem, let me slide her up a little bit here. We have the x-axis and the y-axis top view. We have the point 0, 5. So I already know in this particular problem that my r value, my radius from the origin, is 5 units. And you guys see it? Theta is pi divided by 2, pi halves. So if r is 5 and if theta is pi over 2, then this would be the cylindrical coordinates. Now the thing about polar coordinates we already know is there are other options. You could use theta is 5 pi over 2, where theta is 3 pi over 2 with a negative radius. The rule of thumb is to kind of give the quickest, most efficient answer. If more is required, more details will be given. If you need a specific type of theta, you will be told this. But polar coordinates are not unique. Again, this is not a polar coordinate course. Let's look at one more example. Let's suppose I were going to look at the point. Let's slide her up a little bit here. Negative 4, 0, and 4. Those are my rectangular coordinates. I should have used a different color, but I did not do that. Well, what I do know is that my z value is indeed 4. And if I'm willing to sketch out a little graph here, we got, there's x and there's y, y-axis, x-axis, negative 4, 0 in the xy plane. Well, I can tell you right now that my radius is 4 and my theta is, have you figured it out? That's right, we'll call theta equal to pi 4 comma pi. The z coordinate is a distraction for us. Now if we were to try to draw either of these in 3 dimensions, let me see if I'm able to do that. X, y, z. So this would be 5 units in the y-axis for that one. That one's pretty straightforward. It's on the y-axis. For this one here, x, y, z. Oh, x is negative 4. I have to travel this way. And then I have to travel upwards in the z 4 units. I mean, it might be like right there. It's on the xz plane, so that's 4 units and that's 4 units. But recall in my class I typically don't have students sketching points, But if I provided you a really good 3D version of the picture, you should be able to identify the coordinates. All right. Cylindrical coordinates starts out not too bad. You're going to see some more samples of this attached to the next type of coordinate in space. Until then.